All right. Now, it gives me great pleasure to announce our next format. It's going to be a series of quick-fire lightning talks, more from industry, sharing more about the solutions that they've been deploying and what they've learned. So I think early on in the day, we've learned a variety of use cases. We learned about really innovative startups and AI pilots. We also learned a lot of the chasm, right? It's about how you sell these solutions to scale them. And now I think some of these speakers today come from really large companies, and they are going to be talking about their experience, what their solution does. And so without further ado, I'm going to introduce our first speaker, Dr. Dimitry Tran, co-founder of Harrison.ai, please.
I'm one of the two co-founders of the company, and the other one is my brother, who's a doctor. So he would get upset that if I claim to be a doctor. So I'm not a doctor, but he's also our CEO. There's a global shortage of doctors, and I don't think we need to spend too much time with this audience on this particular topic, other than to say that there's 1.5 million missing radiologists and pathologists globally. The US have the highest number of radiologists per capita, but the US is still missing 14,000 radiologists at the moment. And when you think of a country like India and China, there's 160,000 radiologists currently missing in each of those countries. So this huge gap leading to delay of care, leading a lot of challenges, and the promise of AI has been that it will scale the capacity of healthcare, particularly in imaging, radiology, and pathology. The question that I have is that we've been talking about this for 10 years. Are we there yet? So we start with this morning, there was a very good phrase I want to use called isolated clinical predictions. What does that mean? It means that when you look at something like a CT brain, there's multiple AI on the market here, FDA approved, that can pick up brain bleed, intracranial hemorrhaging. What's the problem with that? That's fantastic. This is an important finding to detect. But the challenge is that brain bleed is not one thing. It is a lot of things. It could be acute, it could be subacute, it could be subdural hematoma. So there's a lot of subtype of brain bleed. So if you just have an AI that is a narrow solution that say there's a brain bleed, it's not very useful. But let's zoom out a little bit bigger. When a radiologist is reading a CT brain, they're looking for 130 indications. Bleed is just one row amongst many. So that's the challenge we have, is that AI at the moment is too narrow. It's only pick up one thing at a time, isolated, narrow solution. And that is the past. At Harrison.ai, we have built an AI. We have cleared this as a medical device in 40 countries. It's pick up all the findings for CT brain. That's what we call the future is comprehensive AI. So here's an example of what AI can look at. For a CT brain, we're picking up the fractures, we're picking up extra blood, vasogenic edema. So it pick up all the findings instead of one or two findings. And my conjecture to you is that if a spell checker that only check for A and B, it's not going to make you any faster with your writing email. You need to check for A to Z. You need a solution that is comprehensive. So that is the present. Currently, we supply our AI to about 10 million patients a year in 14 countries as a comprehensive solution. We have a customer in the room from Germany. On the left-hand side is our AI for chest X-ray. It detects 124 indications, not just pneumothorax, but tension pneumothorax, fractures, free gas, everything that you look for in a chest X-ray. So this image was actually prompted me to including something from Mission Impossible and Tom Cruise. I was watching the movie with my kids last week, and one of the scenes was one of the characters say that he had a tension pneumothorax, and he was fighting an AI. And I was like, that's so funny. Our AI picked up tension pneumothorax. In fact, we are the only FDA-approved tension pneumothorax detector on the market. We have a CAT approval for tension pneumothorax, so very small world. But instead of me explaining how good is our AI, I thought I'd let the BBC spend 1.5 minutes of my 5 minutes to talk about it. Do we have audio? All right. If we don't have audio, I'll verbalize it. Our solution currently is deployed, like I shared, in a lot of countries. Across Australia, 1 in 2 radiologists are using us. In England, 1 in 3 chest X-ray, about 3 million chest X-ray a year is currently benefiting from our technologies. And here is the challenge with the US. We're here in the US. The FDA required 1 finding per submission. So we have 130 indications. It's going to be 135 10K submission. It will take us 15 years to get there under current regulation. And Kurt has been a great voice in advocating for more comprehensive AI, to be clear, in the US. that is why the US AI adoption of radiology is currently lagging Europe, lagging UK, lagging Australia, not because we don't have great technologies, it's because of the delay in getting comprehensive solution to the US. But this morning we talk about the path to adoption or the last mile. The key thing is to get reimbursement. So we recently got new technology add-on payment through a breakthrough device designation pathway with the FDA, and now we get separately Medicare reimbursement for obstructive hydrocephalus. So it's not for everything, but again, every step towards getting reimbursement help the customer to adopt the solution. So that was the past, narrow AI. The present, comprehensive AI. But I think the future is vision language model. Vision language model is when you can use text to prompt the AI to do a lot more than just detecting key findings. So I have here a series of video. I think we have people from, we don't have anyone from Anthropic here, wonderful. We're demoing a demo of our AI against Claude 3. We load in a chest X-ray. We asked it to write a report, describe the finding on this chest X-ray. And I was told that Claude is missing the enlarged heart on this case. But then you can ask the AI to compare to the prior imaging, not just say what is in this particular image. And as you can see, the AI will then write a comparison to describe with the patient history, what does the report need to look like? So this is what we call vision language model, where the AI take in the image, as well as the text, the prompt, the patient history from the EMR, to then write a report. But radiologists are very picky. Sorry, all radiologists in the room. Everyone have a template that they want to say. I say this first, and I say this second. Can you incorporate my template in? It's a very easy job for an LLM or VLM to do, right? It can incorporate different sections, different headings, and then generate a fully written report. Okay, we all heard about hallucination through this whole day. How does it compare? We run a public benchmark with QA-RAT. I think it's a very common benchmark for the researcher in the room. We currently have state-of-the-art, but my disclaimer, this was run last year, so a lot of this model has improved since then, and our model has improved since then. But currently, we have state-of-the-art on the VQA benchmark on accuracy, precision, recall, and F1 score. But I think that doesn't mean anything. Like, you know, those numbers are great for data scientists. How does clinician actually perceive it? So 2 weeks ago at the ACR conference in Washington, DC, and subsequently the result was reported in the SIM conference in Portland, there was a Turing test conducted for 100 radiologists who attended the conference. They were presented with image and report, and they have to decide whether the report is acceptable from a clinical perspective. After they say yes or no, they were presented that it was written by AI or written by radiologists at Mass General Hospital in Boston. And then the participant get a chance to say, you can see that AI-generated report was accepted 64% of the time. Our AI was accepted 64% of the time by clinicians participating in the ACI event. And radiologist report is 79%. So I think we are very close. We're not as good as human report yet, but we are pretty close. So I think the future is here. If you have your phone with you, you can scan this. You can get a demo of our product. I think we like to innovate in the public, so you can try out, or do a subscription, we'll approve, and then you can get to try it out, and would love your feedback on it. Thanks, everyone.
Thank you, Dimitry. That was an amazing talk. And I think just to contextualize why it's so exciting, right? Because I think earlier in the day, you heard a lot of AI pilots and often get asked, hey, you know, but is it actually rolled out at scale? So it's incredible that you already have like over 10 million patients and use case. So next up, we have Kimberly Chun, who is the Global Strategic GTM at North America and Asia Pacific. Cohere, take it away, please.
Thank you. Hi, everybody. I'm going to read from notes just because I only have 5 minutes, and I want to just make sure that I cover everything. First off, I lead growth at Cohere. I work with partners and customers all over the globe, and I have the pleasure and honor of working on the front lines of amazing organizations in all across the world, especially Asia and North America, on their pioneering projects in AI. I'm super excited today to present on the path to agentic AI for healthcare to this amazing audience, as well as fellow speakers. Thank you, Stanford, for inviting me. Cohere was co-founded by 3 friends from the University of Toronto, Aidan Gomez, Ivan Zhang, and Nick Frost. Aidan is actually quite famous. He's our CEO. He is very well known as the co-author of the Transformer paper that Attention is All You Need, which is credited with starting Gen AI. He is also on the Time 100 AI's list of most influential people. We also have an entirely separate organization, Cohere Labs, which is focused on open science research for all over the world, led by Sarah Hooker, and she is also on the AI 100 list of most influential people. Cohere has a strong set of institutional investors, and many of these are also our customers and partners. You may recognize a lot of these logos. We are a 5-year startup with about $1 billion in funding, valuation at about $5.5 billion. We have over 400 employees, and our offices are in Toronto, San Francisco, London, New York, and growing very rapidly across the globe. I myself am based here in Palo Alto, and we have a very big office in San Francisco. So our big differentiation in the marketplace is that we offer models and solutions that are highly accurate, multilingual, cost-effective, and can be customized. And more importantly for this audience, you can launch AI on-prem or in a virtual private cloud environment, enabling the highest level of security, privacy, and compliance. Cohere can also be deployed on any cloud and with NVIDIA and AMD, which allows you to deploy very safely and securely, along with cost efficiencies and flexibility that comes with those choices. I know you're dealing with really highly sensitive clinical data. I didn't hear too much about security and how you intend to deploy, as well as experiment. So we offer a really safe way to be able to do that. For multilingual, we offer 10+ languages for our generative models and 100+ languages for our retrieval models. This enables us to grow really rapidly in AI hotspots, especially across Asia, and we're especially popular in Korea markets, Japan, as well as Arabic-speaking regions in the Middle East and North Africa. So we are, sorry, I think this is my prior slide, sorry about that. So as you can see, this is where we talk about the different types of cloud options. We're very unique in that we're super open. We can mix and match, and it allows you to be deploying very quickly, as well as most enterprises don't have just a single way that you are architecting, so this provides a lot of flexibility, as well as being able to, again, deploy on-prem, as well as very securely in your private cloud of choice. Another differentiation is that we offer very deep custom engineering. AI is not easy. So Cohere offers significant expert custom engineering to enable deployment success. These are some of the organizations that we are in deep collaboration together with. So I'm just gonna talk about a few. For Oracle, we helped accelerate deployment of 100+ features across their most strategic applications, Fusion and NetSuite ERP, that have over 25,000 customers and touches all of the entire back office as well as the front office, including HR, finance, supply chain, and customer experience. For LG CNS in Korea, which is a customer that I personally have been working with, we are building the best performing agentic AI in the Korean language. And within just a couple months, we're seeing extreme progress already. This is the power of really bringing our custom engineering focus to your projects and being very narrow in terms of making sure that we bring the best and brightest engineering resources to you. We're also really popular in regulated industries like banking. And so for Royal Bank of Canada, we are developing enterprise-grade agentic AI for banking for both customers as well as for their banking customers as well as internal employees. For Saudi Telecom, because we're also really, really proficient in Arabic, we are launching agentic AI for the telecom industries and for a lot of the internal efficiencies of intelligent automation, enhanced conversations, and real-time data insights. I bring these examples up because these are really addressing deep engineering as well as collaborations that are applicable as well as transferable for healthcare projects. these are some sample healthcare use cases. We are in very early stage with healthcare payers and providers, and we would love to collaborate with you to progress more healthcare use cases. Some of the examples are fighting disease outbreaks faster by capturing early signals of outbreaks by accurately identifying and summarizing data from thousands of sources and multilingual translations, disease classification needs. We also do a lot of administrative type of AI automation that some of the other panelists had mentioned. We also have use cases with other organizations where it's employee healthcare coverage, helping them get advice on their insurance options, finding doctors in the areas, and answering questions about their medical bills. Also, a health and wellness coach example where you're having a conversational coach that can combine multiple sources of data, whether it be demographics, health goals, and from a library of health and wellness content of this particular organization that's being all embedded into that conversational AI. Fourth example is medical claims processing, where an agentic AI is combining relevant data from multiple sources of medical claims and summarizing and generating specific documents and starting workflows. Some of the examples here goes further to look at health claims that have been denied, and the AI is creating the AI is creating the appeals process with appeals letters and documents needed and starting the workflows. So as far as the path to agentic AI, this is pretty hard stuff. I think there's multiple different types of architecture that you're working on, different projects that you're working on. One of our ways that we're really putting a lot of energy and effort into creating agentic AI abilities for the functional user, not for engineering and technical folks. This is a solution that's designed for business users. It comes all-inclusive as an application. It includes highly performant models, intelligent search and retrieval platform from us, pre-built connectors for standard data sources like Google Docs, SharePoint, Slack, Outlook, Gmail, and custom connectors that you can also build for yourself. So for this audience, it would be really great for any proprietary clinical data that you might have, other clinical data sources. And it's also offered in a modular fashion so that you can mix and match to the models that you prefer. So if you would like to learn more, please give me a call. I'm here based locally, and thank you very much.
Thank you very much, Kimberly. So I know many of you have questions around OpenAI, Cloud A, Anthropic, different models. If anyone has questions, I think feel free to approach Kimberly and learn more. Next up, we have Jayodita Sangvhi, Head of AI Platform at Cohere, please.
Thanks, Ethan. All right. Hi, everyone. My name is Jayodita Sangvhi, and I lead the AI platform at Cohere. I actually did grad school here at Stanford, so it feels wonderful to be back. Thank you so much for having me. Today, we're going to talk about large language experts, which is a combination of LLMs with clinical expertise. For those of you who aren't familiar, Cohere is a virtual cancer clinic, and we do everything from early detection and genetic screening all the way through holding our patients' hands through active treatment and survivorship care. Continuing along with what's becoming the theme of this conference, the big question out in front of us is what is going to be the role of AI in clinical decision making? And we've got this push and pull where on one side we really need efficiency. Already today, we don't have enough care professionals to meet the growing demands in the United States. And we are really going to need some smart assistants to be able to scale access to care for everyone who needs it. At the same time, we also need clinical expertise. There's a reason, for instance, why someone like me can't be a doctor, and that's because there's nuanced expertise and experience required to treat. And many are trying to build LLM models to get to that level of clinical accuracy, but we still do have a ways to go. And so at Color, we're trying to find that balance and hit both sides of this rope. Here's a problem that we're starting with. For a patient, when they first get their abnormal screen, they're typically under the care of their PCP, and they kind of go through the spaghetti. The PCP is helping them figure out all the workup that they need. They get referred to an oncologist, and their office is trying to hunt down all of the records. By the time they finally get to meet an oncologist, usually still some workup is required, so they need multiple visits before they can actually start treatment. We want to smooth this out and help this entire process kind of figure out exactly what workup is needed, exactly what records need to be hunted down, and kind of generate a faster timeline to treatment, which in oncology can really help with prognosis. To do so, we're combining LLMs with clinical guidelines. Maybe some of you in the room are the ones who helped write some of these guidelines. We want to use both of these and avoid the pitfalls of each. So for example, LLMs are known to hallucinate. This is where you do want to use tools or kind of information that really is rooted in clinical expertise. But clinical information is dense and complex, and this is where you really want to leverage LLMs to parse through. So it's about finding the right balance between the two. Putting a little bit more detail into this, we start with clinical guidelines or even a set of layered guidelines and SOPs. And we use this and the structure of those guidelines to kind of turn this into questions, or what are the inputs that need to go in to figure out the actual workup or the treatment that needs to kind of the flow through the guidelines. We take those questions and then search for the answers in a patient's records. And those answers are essentially the clinical decision factors that the system pulls out. Those clinical decision factors then deterministically go through the set of clinical guidelines to determine what the next course of action is for the patient. This could be workup recommendations or treatment recommendations, et cetera. And then lastly, we once again layer on LLM to explain why that is the right course of action for the patient. So it's this back and forth between LLMs and deterministic logic, as well as, of course, human evaluation, and that kind of the balance of that trifecta of methods, which really makes our approach work so well. Let me show you this in action. There's essentially two outputs of our system. I'll walk through both. The first is the clinical decision factors, which we present as a patient summary. Zooming in, you can see that there are parts of the system that are using LLMs, for example, to pull out a quick patient summary or highlight insights. But kind of the root of the whole system is those clinical decision factors that we're pulling out of the guidelines. And they're presented in both a timeline view as well as chips, and we're careful to highlight when information might be missing, inconsistent, or incomplete. And kind of one of the cool parts of the system is that each of those clinical decision factors links directly to the source patient information, which the clinicians love because it boosts trust, and they can kind of make sure the right information is being pulled and they can look at it in context. As the second step, we pull out recommendations for the next course of action for the patient. So here we're showing you what that might look like in terms of workup recommendations, imaging, and labs, with an explanation on the right describing why that is the next course of action. We validated the system with UCSF and did a retrospective study on 50 breast cancer and 50 colon cancer cases, and had clinicians then kind of look at the clinical decision factors and the recommendations to say, would they adjust anything? We found 98% accuracy on the clinical decision factors point of view where they did not need adjustment, and 95 to 96% accuracy on the recommendations, as well as the explanation behind those recommendations. Of course, we really care about that slice that's left behind, and we want to keep making our system better and better, but we think this is a great start. All right, I know that was super fast, so I encourage you to read our paper. You can find it here. More importantly, we are looking for clinical partnership. We would like to keep doing studies to continue to vet the tool for different applications. So if you are interested in partnering with us, please email us at ai@color.com. Thank you.
Thank you very much, Jayodita. That was a great talk. And I think just a quick comment there, right? Just to give a quick example of how much these lines between research and industry are blurring. We actually reached out to Color some time ago to really say, hey, do you have an API that we could actually use to bring in clinical guidelines? And we're quite impressed, having met many vendors, that they actually had a market-leading solution that we are hoping to adapt for our use case. And now moving on, we have Dan Golden up next. As you may know, MedGemma, Google's open weight models, were released recently. It's a lot of fanfare, so excited about this one. Dan.
All right, thank you very much. So I'm Dan Golden, and I'm going to be talking to you about what we're doing at Google to accelerate the health AI developer community with open medical foundation models, and specifically with a new one that we released just in the past couple of weeks, MedGemma. So the health AI research team at Google focuses on catalyzing the adoption of human-centered AI in healthcare. And we do that in two different ways. One is by showing the world how to build safe and effective AI through our own research studies, and the other, which I'm going to focus on here, is in enabling others to build AI for healthcare via open weight tools and open source tools that we release. So the way we're doing that and releasing open tools is through a program we call Health AI Developer Foundations, or HiDef. This is a suite of open models to accelerate the development of AI in healthcare. The program has been around for about 9 months, starting in November 2024. And we've already released several medical embeddings models for several different imaging modalities, bioacoustics, and so on. But then this year, we started releasing LLM-based open models. These are derived from Gemma, which is Google's open version of Gemini. And the first one we released about 3 months ago is TX Gemma, which is optimized for therapeutics. Then just 2 weeks ago, we released MedGemma, which is our open weight model optimized for medical image and text understanding. So MedGemma is a suite of 2 different models, a smaller 4 billion parameter model and a larger 27 billion parameter model. The smaller model is multimodal in nature. It can read and understand radiology, dermatology, digital pathology, and ophthalmology images. And then both models are optimized for medical text as well, with the 27B model being a thinking model, so further optimized there. These models are medically tuned, so they have custom, the 4B model has a custom image encoder for medical images. Both models were customized for text as well. We have evaluated them, and they achieve high performance, with performance approaching that of much larger API-based models. And importantly, they're open to all. And we think they're an ideal starting point for developers that are working either in medical research or in medical applications. Regarding performance specifically, compared to Gemma, our base model, we see a 40% or more average improvement on image-based evaluations and tasks, and a 20% average improvement on text-based tasks, highlighting the importance of tuning these models for the medical domain. Here's an example of the cost per performance curve for our models. On the y-axis, you see a common text-based evaluation, MedQA, where the higher values are improved performance. And then the x-axis is the inference cost. And you can see the MedGemma models, which are in orange, show a very good ratio of performance per unit cost, approaching that of much larger proprietary models. So crucially, MedGemma is completely open. Compared to the big API-based models, although it may not perform as well as the largest of those models, it has significant advantages in several different situations, where a researcher or developer needs substantial adaptation for improved performance in their domain, where they need data to stay on site for privacy or as part of their organizational policy, where they want to use the models in an offline use case, where internet availability may not be present or may be flaky, where inference costs are a particular concern, given the models are particularly small in this domain. And then finally, where the developer wants to create a medical device, which is permitted in the MedGemma license, as long as the users appropriately adapt MedGemma for their use case and evaluate them. We've worked very hard to ensure that MedGemma and these other models are very easy to download and easy to use. You can download them from Hugging Face, the standard open site to get these open weight models. And then we've provided a lot of different example tutorials and code examples, both for running inference and for fine-tuning these models for specific use cases. If you want to learn more, you can visit our sites at this URL. You can also email us at highdef@google.com, and we're really looking forward to what you all do with these models. Thank you.
All right, thanks so much, Dan. Finally, we've got Krishnaram Kenthapadi. He's the Chief Scientist, Clinical AI at Oracle Health, here to tell us about some of the exciting things Oracle Health has got cooking up in its lab.
Thanks, Ethan. Thanks, everyone, for joining today. It's my great pleasure to share some of the lessons we have learned in the process of building and deploying agentic experiences for clinicians. So as we all know, healthcare providers across the world have been experiencing a burnout, causing them to seriously consider quitting their professions. A main reason for this burnout is different kinds of administrative burden. A doctor might be spending 1 hour to 2 hours each day writing clinical notes, searching for information about the patients, and so forth. Nurses may be spending a lot of time performing data entry tasks. Often, a doctor may want to combine information from many different sources in their brain if they want to figure out something about the patient. So our goal is to help reduce many of these tasks, provide an assistive way of reducing these tasks so that the doctors and other clinicians can spend more of their time providing care and connecting with patients. With this goal, we have been building voice-first agentic experiences. So this is part of the product called Clinical AI Agent that we launched a year back. So this is voice-first in the sense of being able to talk to the EHR. It is across different modalities, from being a mobile app to web app, desktop app, and so forth. The idea here is that we want the AI to be largely invisible, like what was being discussed earlier today. We don't want AI to be one of the things that kind of affect the way a physician interacts with these systems. We want AI to be a way to simplify the workflows, to make things more efficient for the physician, and so forth. And the way we are heading towards this is like starting with aspects like generating clinical notes or helping generate summaries, helping perform searches, and so forth. We want to move towards a region where the AI systems are more proactive. Perhaps when there is a new lab result, there is something that triggers, and the AI agent provides some indications to the physicians, and so forth. So today I'm going to highlight one key component of the system, just to give you a feel for what are some of the challenges involved. This is what we call as the agent orchestrator. So this is a component that interacts with many different agents. These agents could be user interface related agents. These could be data retrieval agents, or this could be search agents. This could even be guardrail agents to decide whether the query that a physician is asking could be allowed or not. As an example, at this moment, we do not want the clinical AI agent to provide medical advice to the person who is asking the query. So let's take one example. Let's say that a physician is looking at a patient and wants ask the query, show me her recent labs. Depending on the context of the application, this could be something as simple as retrieving the relevant UI element and showing that. But in case that's not the case, we may want to perform a search against the past medical records. These could be present in structured information. This could also be present in free-form notes, and so forth. And then decide how to stitch all of this information together. Decide whether we want to, whether the information that is retrieved is of sufficient confidence to present back to the user, or do we need to perform further searches, further actions based on that. So this is all part of the multi-agent orchestrator. And in addition to the application context, it also takes into account the history of the conversation. So perhaps once we see the labs, we may want to ask, just show the abnormal results, or how have they differed or deviated from the labs 6 months back, and so on and so forth. And so this takes into account the patient context in the form of the patient history, as well as the context of the application and the conversation history. So next, I'm going to highlight some of the lessons we have learned in the process of doing this. As has been highlighted in many of the talks today, we have been focusing not just on the model development, but also on ensuring that the quality of the data is high, and deciding on the evaluation methodology upfront. And to do this, we engage closely with domain experts. These could be domain experts at early customers who are willing to give us thoughtful feedback and perform evaluations in a controlled setting, and then give us feedback so that we can further improve the systems. This also help us decide among so many different functionalities we could be building, which ones we want to build first, which ones are the need at the moment, which ones are the things that are likely to become important going into the future, and so forth. And the approach we have been following is one of iterative development and deployment, where based on the feedback, we make further improvements, learn from mistakes, and then decide whether something is ready for subsequent deployment or not. So in addition, we all know that LLMs are not going to be perfect. How do we recover from the errors made by LLMs? That's one of the things that we spend a lot of time thinking about. One way we have been doing this is by encoding the task-specific and domain-specific knowledge. This can be in the form of semantic knowledge bases that takes into account the patient history, as well as publicly available medical knowledge, and so forth. And most important, I believe that ensuring trust, the safety, and observability is very important, not just from a legal or regulatory angle, but also for building customer trust, retaining that trust, and enhancing that trust over time. To just summarize, I want to emphasize that we want to not only focus on aspects like correctness, but also robustness, or bias and fairness, security, transparency, and so forth. And even after we deploy the system, as we heard again and again today, it's important to continue to monitor all these aspects, not just the quality of the system, but also whether the system is starting to show new types of biases, whether the system is degrading in performance for certain subgroups of users. How can we detect those issues early on and take corrective steps, and so forth. We have been exploring different aspects of this. I have added a few links to some of these papers and talks. So if you're interested more, I would love to discuss more, and looking forward to collaborating with all of you. There are a number of exciting open research problems that we face in the system. As an example, as we move towards more complex agentic frameworks, how do we detect failures? How do we perform evaluations of the agentic framework end to end? How do we gracefully recover from failure modes? Can we have graceful fallback to perhaps more deterministic workflows when some of the generative AI-based workflows do not work as well as intended? There are a number of such research problems. I'd be more than happy to discuss offline, and thank you all for listening.